Good morning, everyone. It's our last day of our fifth Wombat workshop. And we have our keynote, Claudia again, Claudia Sagastizábal, and she will tell us about exploiting structure in non-smooth optimization, present and future. And I guess we're going to learn more practical things today, continuing from her talk yesterday. So please, Claudia, go ahead.
Okay, thank you. Hello, everybody. Hello from Rio. It's a nice today here. Okay, so I had some depth that I will talk about if Regina is there. Otherwise, I will leave it for when she comes. I think she's not here yet.
I'm
so
here. I'm here.
You're here? Ah, okay, okay.
Yes.
It disappears. Things disappear when I go into the presenter mode. I cannot see. There is something I'm not doing smartly with Zoom. But well, anyway, okay. So then my first slide is the depth from yesterday. So I went to look at the paper and to see what were the conditions, and we had a problem, an equilibrium problem with equilibrium constraints that arises in energy markets, where in the upper level, the generators try to maximize profit, and their decision variables are prices and bids. And this is a bilinear problem. I forgot to say that, but it's bilinear because the price is also that there will be this also decision variable, and is multiplying the quantity in the objective function. So this is what makes challenging all this, the solution of those equilibrium problems. And then in the lower level, the bits that they send to the of quantities and prices are being taken all together by the independent system operator, who solves a system. Here on the right, you can see suppose beta is 0, then it minimizes the total expense with the L is the how much it will be dispatching each generator for the price that was bid by the generator. Here it's a variable for this lower level problem. The sum of all the dispatches has to satisfy the demand, and so the multiplier of the demand constraint is the price that will be paid to the generators, independently of the price that they bid. But usually, not usually, the multiplier is larger than the largest price that is being bid of the dispatch agents, of all the agents that are being dispatched. And this is the marginal agent is the one then that commands how high will be this multiplier here. And this is why, to prevent the effect of pushing up beyond the bid of the marginal player, the marginal price, the price that is going to be paid, that is a multiplier of the demand constraint. There are a lot of marginal and prices over here, but well, that's the way it is. So in order to prevent this effect, we propose to introduce in the dual, we wrote the dual of this problem in the lower level, because here everything is linear, there is not a duality gap. And then we introduces a penalty that is controlling how large is the marginal rent. The marginal rent is the multiplier. Here I forgot one constraint. So it's L smaller than G. It's because it's here. It's L smaller than G because the ISO cannot dispatch more than what the agent proposed to generate for the price that was bid. So the multiplier of this constraint is what we call lambda, and it's called the marginal rent. Is some extra amount of money that because you see the price that will be paid depends on the bidding price and on this marginal rent. If this marginal rent is large, the price will also be large because we are trying to maximize here in the dual. So this marginal rent is something, when it is called rent in economy, it means that it is obtained without effort. And here it's without effort. It's just for because the price that is being bid by the agent is lower than the price that is paid. And this difference is the marginal rent. And if the most expensive agent that is dispatched, that is the marginal agent and the one that I represented by a shark in the drawing yesterday, in the diagram yesterday, if this marginal agent has marginal rent, it has a lambda that is non-zero, then the price, the equilibrium price P will be higher and higher than what is strictly necessary, because the less efficient agent, the one that is the most expensive, should not be rewarded for being the most expensive, which is in economic terms what it is happening if the marginal rent of the marginal agent, this lambda, is larger than zero. So in order to discourage this type of rent out of nothing for the less efficient generators, we propose to penalize in the lower level with this function h. And yesterday I presented this function as the infinite norm. It can be any penalty, that was the question. It can be a convex function, non-negative, that is 0 and 0, and satisfies conditions that are typical for penalties. And then if we look at the dual regularized problem in the lower level, and we let beta go to 0, the penalty go to 0, then we can show that the sequence of prices and rents, P and lambda, converge to multipliers of the original dual lower level problem, and with the property that the price is the smallest one among all the set of multipliers that are associated to the original problem in the demand constraint. And this all is interesting and it's important, and it's general for any penalty of this type. Now, if we want to look what happens with, because this theorem doesn't say anything about the dispatch, what happens with the dispatch that you will be the ISO will be decided, that corresponds to multipliers in the dual form or in the primal form here, the decision variable. What happens as beta goes to 0 with this limit? And for that, we need some additional assumptions on the penalty, because they have to be satisfied, these conditions that they have to be satisfied by the conjugate. We use Fenchel duality for this kind of results. And then the conditions are, well, here it's, and they are satisfied by the L infinity norm and the L1 norm. It's dual norm. And in this case, if we use then a proper penalty, then we can also have not only the price that we will get at equilibrium is a solution of the original problem, but also the primal dispatches, which is also of interest. What is also of interest here is that since we had with beta equals 0 a linear programming problem, if we add a polyhedral norm like the 1 norm or the infinite norm, we will not be disimproving the structure, this linear structure in this lower level problem, and this makes things easier in some sense. It can also be the question of Regina Voss, if it can be a quadratic, a norm square. Yes, it can be for this result, but we will not be able to say things about the primal, which is consistent with all the fact that the quadratic, for example, term in an augmented Lagrangian will not be exact. It's well, it's related to this kind, but this is explicitly what we need in this setting. Okay, so this is my depth from yesterday, and then I will continue with our VU considerations today. And actually, it is not bad that we cut into the presentation, and today is supposedly to be shorter so that we have more time for discussions, because after my talk, there were talks that where there were more things being said by Dima and by Shane about the VU decomposition. So it is welcome also for my talk today. They were happy that I mentioned them, did it before them, and now I'm happy that they mentioned it before the second talk. Okay. So this challenge that apparently was, there was somebody who responded to the challenge, but I couldn't see yet we will see afterwards. What was the response was Okay, you have this function. This function depends on a parameter alpha, and today this parameter alpha will be important because for alpha equals 0, here I put it in the open 0, 1 interval, but for alpha equals 0, things are not that good. And even though, look, it's a very like innocent and naive function, it's a maximum, if alpha is equal to 0, is the maximum of the norm square and the second component. It's really not too difficult, but this function, when alpha is equal to 0, fails to have a proper second order, which is what we will try to identify and to introduce in order to have fast methods for minimizing functions that are non-smooth. They have to identify not only paths of smoothness, but also try to go fast and to mimic a Newton method along these fast tracks of these smooth manifolds. Okay, so here we have a graph of this function, and where the kinks are, where is not the non-differentiability of f is where these two terms are equal, and this happens in a circle of radius alpha plus 1 and center at 0, 1 or something like this. Okay, so if we rotate a little bit this function, we see that it has this sharp behavior when it's looked from the proper angle that Dima was mentioning yesterday. It's and outside of this manifold of smoothness, there is this sharp behavior. And if we rotate it more, we look at from what would be on the left graph from the left, then we see that it really looks nice. It looks like a quadratic function that if we were able to identify this manifold here or this region here, and we could follow this function, this region, then the function would look as if it is a pretty quadratic, and we could happily apply the Newton or the Newtonian method to converge fast. Okay, so from where all those ideas come, they are not new. This is the oldest reference I could find. It's a report from INRIA, because in the past century, this used to be the way of doing things. Now we put everything in archive or in some preprint server and it's available, but this was the way we used to do things. It took 2 years or more to appear in SEOP. Here is the reference, this paper. So in this work, we tried to answer the following question. The Moreau-Yoshida regularization, or the Moreau envelope, is a regularization, and for a function that is lower semi-continuous and convex, since we're speaking here of Moreau-Yoshida, it gives you a mapping that is of class C11. It has a Lipschitzian gradient. But to apply a Newtonian method, you need a little bit more. You need to have at least a Hessian in the limit point. So what happens in that sense when this extra level of regularity or smoothness is present in the regularization? Okay, and then if we start looking with care a little bit, this was instructive to realize what kind of things were going on. This function, here you have this outer circle is where the first function, the boundary of where the first function is active. Here is where the second function is active, and in this crown, here both of them are active. And where the function is non-differentiable is in this circle here. So in all these points here, these are in this crown, sorry, is where the proximal point lies in this kink of non-differentiability. Also notice in this drawing that if alpha is 0, then this outer circle will touch the trajectory of non-differentiability, where there is a non-differentiability of the function. Okay, so This is why we're using a positive alpha. Okay, so the interest of this thing is that of this problem is that we can compute explicitly the proximal point and play with that. It is in this article, and it's here I reproduce. It doesn't really matter much what is the expression, except that for all the points in this crown, another thing, this function is minimized at 0. And at 0, the subdifferential is minus alpha e e. Okay? If alpha is 0, 0 will be in the boundary of the subdifferential. Okay? So, and this is what complicates things later on. But if alpha is not 0, then 0 will not be in the boundary. It will be in the relative interior of this segment that defines the subdifferential at 0. And this is when good things happen. Okay, for all the points in this crown, these are this z of x, the proximal point has this expression, and it is here. And the interest of this expression is that we can compute derivatives, we can do things very explicit that we cannot often do with usual functions. Okay, if, as I said yesterday, if we have perfect knowledge of this function, so we can compute explicitly the proximal point, we can compute all the subdifferential, and we can do the VU decomposition that I didn't say explicitly what it is. And if we do that, and we generate 1,000, 10,000 starting points, and we run the proximal point method or this enhanced proximal point method with a Newtonian step in the U subspace, making this VU decomposition, then we have a formidable increase in accuracy. Here is in red all the final points that were obtained, how many digits. It's 10 to the minus 16, and here with the other one is 10 to minus 5, having the same stopping test. And well, here is the number of iterations that doesn't say much, except that because it can one iteration of the VU enhanced prox method is more bulky. There is more work to do than just computing the prox. After computing the prox, you do some Newton correction. But since this is a problem that is of dimension 2, it is negligible. It's practically the same. And you can see that, well, there are much more iterations with the proximal point method than with this enhanced proximal point with the Newton flavor. And this is achieved by exploiting what I called yesterday this implicit structure, the hidden smoothness, trying to identify this manifold of smoothness that Dima was mentioning yesterday. Okay, how is it done? So let's fix notation. We have our function, a prox parameter mu, and this capital F will denote the Moreau-Yoshida or the Moreau envelope. And as also, I had this drawing also before in the one Chain showed his, but he used the same example. This is the Huber regularization of the absolute value that is nothing but the Moreau-Yoshida or the Moreau envelope of the absolute value function. And the unique minimizer of the Moreau-Yoshida regularization of this of the minimum that defines the Moreau-Yoshida regularization or the Moreau envelope. Sorry, I will try to stick only to one line. So this gives a mapping that is the proximal point mapping, right? That depends on mu, on the step, and of course depends on the function. And this is a smoothing, or this is a regularization, which is has a gradient that is Lipschitzian, and the gradient of the envelope is mu times the point minus its prox. Good. Okay, so minimizing f, then it's equivalent to finding a fixed point of the proximal point mapping, because sorry, here if we minimize the envelope and constraint, this is equivalent to finding a gradient that is 0, and this is the same than saying that x is equal to its prox. Okay, and this is equivalent to minimizing our original function. And then if we do well, the proximal point method is nothing but the Picard iteration for solving a fixed point problem. We will compute successively the prox mapping of the current iterate. This will give us the next one, and so on. Okay, if we remember what here I wrote what was the gradient, just to not to forget. Of the Moreau-Yoshida was mu x minus the prox. So if we add here plus minus x and multiply by mu divided by mu, we have this equality. And now we remember that this is the Hessian of the, the gradient of the Moreau envelope. And then we see that in fact, the iterates that we are doing when we do a prox iteration is nothing but a gradient method on the Moreau envelope, preconditioned by the inverse of the proximal step. If we were to use, instead of a prox step, a metric for defining the quadratic norm that defines here the Moreau-Yoshida, if here we have some matrix, a positive definite matrix, or can be even positive semi-definite, then we would have here the inverse of this, and then we would see that this is then what we are doing when we do a proximal method is to make a gradient step in the Moreau-Yoshida, in the Moreau envelope, preconditioned by this proximal step or the proximal metric that we are using in the quadratic term. Okay, so gradient methods are not fast. If we want to accelerate a gradient method, we should go into the Newtonian world. And then we should, instead of using this 1 over mu, try to put some curvature of the function that we are trying to minimize. And this is amounts to say, if there is a Hessian, the inverse Hessian of the Moreau envelope. Okay, but we know that the Moreau envelope is C11, it's not C2. So this is how it all started. What happens then if we have a convex and lower semi-continuous function? We know the envelope is C11 everywhere. But now what we showed is that if the envelope is C2 everywhere, if we ask that there is a Hessian everywhere, then this means that the original function was already twice differentiable, and then, well, there is no point in doing all these, applying all these tools, because we could have simply done a Newton method on the original function. So everywhere we cannot go. This is a negative result. We need to think in a different way, and from now on, I will forget about mu, and I will write only capital F. It's the Moreau envelope with a parameter mu. Okay, so what happens if instead of trying to find a Hessian everywhere, we require that at a given point x0, there is the Moreau envelope has a Hessian. Okay, what we showed is that because of the form that the gradient of the function has, there is not much to show here, is that the Hessian of f exists if and only if the proximal point has a Jacobian there. You need the Jacobian, the proximal point to be to have a Jacobian. Okay, and then when there is a Jacobian of this proximal point mapping, the image of the Jacobian is contained in a very specific subspace. It's not in the whole space of Rn. It's a very specific subspace, and this is the subspace of smoothness that generates this U subspace that we are eagerly trying to identify. So for our function, well, here I wrote very little For all pointing these crowns, you can, well, with those formulas that I gave, you can compute the proximal mapping and its derivative, and eventually it is perpendicular to a vector that I defined before that in fact generates the space of the subdifferential of the function at the prox. So the image of the Jacobian of the prox is in this manifold of smoothness that we are trying to identify. Good. So the idea is we can then try to follow this manifold and make a correction of the proximal point that was slow by making a Newton move, but only in this subspace, because it's where we will have second order for our regularization. So we showed in a work with Bob Mifflin that making a proximal point plus a correction in this subspace, in fact, amounts to making a Newton step for the Moreau envelope, which is what we wanted. So we have to work into a subspace. Okay, and then as I announced here, if this subspace and the second order for the Moreau envelope for this example, and the proximal Jacobian of the proximal point will exist at 0, that is x0 here is the minimum that we are interested here in approaching asymptotically. It will exist, the second order, if here we have a space, if alpha is positive. For the apparently innocent function with alpha equals 0, we cannot do this this kind of decomposition. And what happens is that when alpha is equal to 0 and the 0 subgradient, which is what characterizes optimality, is in the boundary of the subdifferential, then the V and U decomposition will not generate subspaces but cones. And then, well, then things are not anymore as nice. So the question of second order for this kind of degenerate case is not for this really nice looking function. It is non-differential, but has not nothing too nasty apparently, but with alpha equals 0, it is nasty and we cannot deal with it. Okay, so what is the key? As I said, to track this region where there is the non-smoothness, we need to decompose the space into 2 orthogonal subspaces. On the V subspace, the function is sharp. On the U subspace, the function looks smooth. And how is it that we concentrate all the sharpness of the function? Well, it's just by generating V as the linear subspace associated that is generated by the subdifferential of the function. This is, in fact, if you think of this type of functions are like if you have an open book, the graph, and then this open book walks through a parabola, right? So if you are all the time walking along this ridge where the book is being folded, you will not see that the function is not differentiable because you will always see the parabola. You have to get out of this ridge of non-smoothness to see that it is sharp, that there is a sharp change there. So parallel to the subdifferential, all this non-smoothness is concentrated locally. This is local analysis, and the subspace that is perpendicular to this V subspace is the U subspace, is what we are looking for. Good. So now we are almost done. So we need to land on the smooth manifold. And once we are on the smooth manifold, we need to make a Newtonian move. And for that, we need to define a tangent, the red arrows, a tangent direction that will allow us to move fast into the minimum direction of the minimum that is here. So we need those two objects, and this is an important realization. So the method is primal and dual. We need a primal point to land in the smooth manifold, and then we need a dual element that is related to a subgradient, or would be in a smooth setting, it would be, this would be given by minus the direction of the gradient of the function at that point, right? Here we need, we will have a special subgradient. So, and then this is the dual part of the primal dual method that we need to devise. Okay, so for that we have then some theory that is behind, and one important one is that as in our example, when we are near the optimum or a stationary point, but here I'm speaking only about convex, although the results hold also for non-convex functions. The proximal point lands on this fast track, on this manifold of smoothness. So this can be proved. So if we are able to compute the proximal point of a function, we will be following this value of smoothness. We will identify this hidden region where the smoothness of f lies. And then to define the tangent direction, what we will do, once we are in the point that is smooth, we need to find a minimum, we will find the element of minimum norm in its subdifferential. And what here is stated, what is exactly what we mean, that the proximal points are on the fast track, for those who like formulas more than hand waving and drawings like I'm doing here. So we have a primal step that will take us into the U subspace. And then we'll have, using the tangent direction, we will get out of our U, of our smooth manifold, but we will do that using a tangent direction and with in a Newton-like move that will make us converge fastly to the minimum. Okay, so if we have, for that, notice that we need to have perfect knowledge of the primal and the dual objects. And this amounts to having, to being able to compute the proximal point and to being able to find an element of minimal norm in the subdifferential. So we need to be able to compute the proximal point, and we need to be able to know the full subdifferential. In the examples that I was talking about yesterday, where we have a function that is a value function, this is just not possible. Okay, this the knowledge we have is not the whole subdifferential. We know one multiplier of the optimization problem. With that, we build one subgradient. That's why I was speaking of black box. Here, we need to have a perfect knowledge of the first order information of f. But if we are lucky enough and we have this perfect knowledge, then how the algorithm would work? And this is the algorithm that I coded in this challenge. Compute the proximal point of the current iterate, then compute its Jacobian that we can because it is explicit, and then check in which subspace it is, and this will give us the Hessian. This is like the gradient, the Hessian of the Moroi-Yoshida is mu times the identity minus the derivative of the prox. The subspace of smoothness that we are looking for is spanned by this Jacobian. And then with continuing with the perfect knowledge, we will compute the element, we will project 0 into the subdifferential of the function at the proximal point. All this, we can do it in this function. And once we will do that, we improve our proximal point with a Newton type move. We make with this curvature, and this is just to bring it to the right subspace if it was not there. And then when do we stop? Because it's important to know when to stop. We stop when the norm of the move of the U move is small enough, or when the prox is sufficiently close to the iterate, because then it means that we are close to the optimum. And then doing these calculations, implementing these calculations for this function that is perfect knowledge, then I got this fantastic performance. Okay, so now, but the world is not so perfect. And what happens if we have imperfect knowledge? If we have imperfect knowledge, yesterday Chain explained to us how to approximate the proximal point of a function with any desired accuracy by using a bundling mechanism. And what we will do is, instead of computing the proximal point of the function, we will compute the proximal point of a model that will be built with linearizations that were obtained by calling the black box at past iterates. And this will give us, for example, this is a possibility. There are other possibilities depending on the structure that we know of the problem. As I was saying yesterday, different types of black boxes. But, well, we have a model of the function. We don't have the function. So we need to approximate the proximal point. So for the second step, we also will make approximations. Sorry, here is, I put the post here in the wrong place. So then instead of minimizing, projecting zero into a subdifferential of the function that we don't know, we will have an estimate of this, we will have a subdifferential of the model function. And this will give us the approximate dual element. And with this, we will be able then to generate an approximation of the U subspace and of the second order, okay? And then we will do our Newton move, U-Newton move, approximate everything, because we are approximating with the model our function, because we don't have perfect knowledge. Okay, since we don't have perfect knowledge, then we need to know when the model is not good enough, and we need to improve it before starting doing all these calculations. And this is what is done by the mechanisms of serious steps and null steps in the bundle method. I don't want to enter into more details here. It's those who know what it is will understand, and those who do not know, just believe me, it is a way of deciding if the model is sufficiently good. If it is not sufficiently good, we need, for example, to add more linearizations before we start doing computing an element of minimal norm or doing a U-Newton move. Okay, and this mechanism, this imperfect, this view algorithm with imperfect knowledge is what we apply for the function that I showed, this half and half function that was the square root of a quadratic semi-definite form plus a quadratic form, and is what gives this very fast convergence. And we prove that the convergence of these steps, the proximal points that are being generated in this sequence, when we do serious steps, so when we do this U-Newton move, there is superlinear convergence. Now, you will see here, so those are those points here. Those other ones that are like a clump of points where we do not have good improvement, where we have here superlinear improvement is from this one to this one. But all those here didn't give any kind of improvement. Those are the null steps. When we were improving our model until it was sufficiently good and we could do a superlinear move. So this is the explanation of this zigzag that we observe in this plot. Okay, so imperfect knowledge and perfect knowledge. Is there something in between? And this is when I'm getting to the end of my talk with some open questions. What happens if we have partly perfect knowledge? I'm not sure. I don't know what happens. This is what I want to bring here for discussion, a reflection. So suppose that we have a function with composite structure where we have a convex, non-smooth, easy function, for example, the one norm, the absolute value, if you want to think it. And inside, we're computing, so the one norm of a smooth mapping. So this is similar to the case where we had a max function of a smooth mapping here, for example, the one norm. And so all the non-smoothness in this problem is concentrated in this function h, that it's a norm, so well, it is support functions of linear, has a lot of properties, but it's non-smooth. Could we design a view algorithm with partly perfect knowledge? So this means, well, for example, we have to separate then the action of h and the action of the smooth mapping. So we'll write the vector of that is the image of the smooth mapping. And then the subdifferential of the function is the Jacobian of this vector transpose the subdifferential of the non-smooth function at this point C, the image. Okay, so what I'm saying is, since this function is easy, we may aspire to have perfect knowledge for this one, because we can compute the exactly the proximal point of the one norm of a vector C. It's like it's just an extension of the Hoover. And then we also can know exactly the subdifferential of the one norm. It's of a vector C. So this is something that we can afford, let's say. It's not too expensive. And the questions are, is there some relation? Because we know how to compute exactly the proximal point of our function h at the image. What can we say about the proximal point of the composition? Is there some relation? Because we also need the Jacobians and the U objects that come with that. Is there some relation that we can establish in this setting? Knowing this is an important relation. So could a Taylor model for C be used, since it's smooth, and then we don't care about much more than the first, eventually second order to get some curvature, but no more. So I don't have answers for these, except some ones. We were studying for some time with Leo Shuai Liu, who came for a postdoc, was a student of Andrew, came to Brazil. And then there are some relations. We know that the v-subspace of the function can be defined from the v-subspace of the h function, just by pre-multiplying by the Jacobian transpose of the smooth mapping. So also, if we were to use a model like is done in the prox linear or prox descent method by Lewis and Wright, maybe we could think of approximating, using as a model, as I said before, the model of the function in the perfect knowledge VU algorithm, the linearization of the inner mapping and compose it with h, and that will give us a model for the function, and then maybe we can relate the proximal points, and we need to have some asymptotic result. And for that, it could be useful perhaps to use some enlargement. This is in sync with what Russell was asking yesterday. For example, the epsilon subdifferential of f, it's too big. It's too big. And we don't need the epsilon subdifferential of the composition, because what is introducing discontinuity here in the subdifferential is not the smooth mapping. It is the subdifferential of the function h. So perhaps we can use the epsilon subdifferential of the function h and pre-compose it, then pre-multiply it with the smooth mapping, and then this generates some epsilon subspace that is enlarged maybe, and because of the continuity properties of the epsilon self-differential, we can say something about what's happening with this VU, the composition space, as epsilon goes to 0, and we converge to the optimum, or to converge to X bar, let's say, to the accumulation point. So these are my questions, and also, well, of course, once we know what happens with the Jacobians, we can say, we can see what happens with this Hessian, with that is a part of the Moreau envelope, and this is what is represented by the U-Lagrangian. All those who have heard about the U-Lagrangian, I decided not to speak about the U-Lagrangian here, just to speak in terms of the derivative of the proximal point. Okay, so all that then also brings me to my one but last question. That is a citation that I will read with my French. I don't know how many, there is Julien, I think only, so not everybody will be offended by my massacring of French. Existe-t-il une généralisation adéquate de la notion de Etienne? Cette question est la plus passionnante qui se pose actuellement, et une réponse satisfaisante marquerait probablement pour longtemps une étape décisive dans la recherche fondamentale en programmation mathématique. Okay, now that I massacre your ears with my French, let's continue with English. This citation is from Test d'habilitation of Claude Le Maréchal from 1980. And it says, does an adequate generalization of for the notion of a Hessian exist? This is today's most interesting question, to which a satisfactory answer would probably start a new, long-lasting and decisive era for basic research in mathematical programming. And well, it's some kind of holy grail, and since I had put some pre-Raphaelite pictures for my open box there, opening the black box, I decided to close it also with one of the same painter. It's kind of the holy grail. We need introducing sound concepts. Sound, I mean computable, because I'm a computing lady. I like to crunch numbers and to make iterates and to compute in algorithms the numbers, the objects. So we need objects that are computable and that can be estimated by an optimization method. And this VU and going into this direction sounds promising, especially if we can take advantage of structure. For example, perhaps all those appear in machine learning, the one norm or one that along those lines where the prox mapping is easy to compute. Okay, and with that, I finish my talk. I didn't leave much time for discussions. Well, we'll have 10 minutes for discussion. Thank you.
Thank you very much, Claudia. So are there any suggestions, questions for the discussion? Matt?
Yeah, thanks, Claudia. I have a question about how you say, for example, comparing the proximal point algorithm to the VU algorithm. I understand this first example is a Tory example, but maybe the same comments apply more generally. So if you compare, so you're showing some kind of superlinear convergence in the number of iterations in the plots, but this could be offset by the fact that each iteration of the VU algorithm is much more expensive to compute. All right. So I guess my question is then why not show the time? Because surely that's in practice maybe more important than iterations.
Yeah. It is nothing. In this case, it is a 2x2 matrix or a 2x1 matrix that is identity here. Sure. So I either compute the prox, that is an explicit calculation, or I compute the prox minus some term that it's a vector eventually. So it is not, in this case, it's not meaningful, but I agree that it is meaningful in higher dimensions, which are the ones that are challenging, in fact. And it all boils down to a question that is the first question I ask when there are those people who come for consulting or something. What is your output of interest? What are you interested in? So if you are satisfied with some few digits of accuracy, there is no point in doing in killing a mosquito with a missile. This is a missile that is too strong. I don't know. For example, in combinatorial optimization, you would use a dual information to cut off some regions. Then you don't need much accuracy, and then then you don't use this kind of methods. When it comes to electricity prices, maybe yes. You say you want more accuracy, so it depends. It depends on that. So it depends on. So I didn't put it here because it was really, for the example, it is too much of a toy example. But for a more significant example, yes, you have to compare accuracy and you have to compare CPU time, the time that you spend.
So just to follow up very quickly on that then. So if this toy example, instead of being in R2, was in R100 or R1000, how does and you could still compute everything, then how would the times compare?
I don't know.
Was 100 dimensional or 1,000 dimensional?
Yeah, I don't know.
Okay.
Can you compute I would have, all those calculations are done in R2. By the procs, the explicit procs. I didn't try. Perhaps I could try it. No, I think. Let me see. Yeah, I stayed in R2 because I could make drawings, etc. But wait, here, it's probably, I don't know. Here, oops, where is the next one? Sorry. So here, so maybe I can do in Rn. And the procs. Yeah, I will try. It's I thought of this example on Monday, so I didn't have time to do. And I started in Python. I learned Python during the quarantine. That was useful for me. And then I started in Python, and then these wireframes and all that I made there. But then to do all those calculations, I went to Octave and Scilab because it's what I have installed and I know better. But now that I have more time, I will try in Rn. You are right, and then we can try. We can compare. Perfect information.
I have a question, Claudia. I've often wondered with the UV method. It usually the analysis is based upon the idea that there's like a single trench along which you're sort of following the path, but you could imagine that in fact the U space could bifurcate into two branches, and one could descend more quickly than the other. And I was just wondering, do you have any intuitions on how these methods might respond to the way in which the dimension of the U space might change, or the way it might bifurcate and things like that?
This type of situation probably arises in non-convex, right?
Yeah, I would think so. Yeah, that's right.
Yeah, in non-convex, what we do, and we'll have, we never published that, but we should do with Bob. You need line searches to try to, and the line search cannot be any kind of line search. You need to make some, well, you have to pay attention how things are, because the V subspace can be a V that is flat on one side and then on the other one side is curved like this, and this puts you into trouble if you don't do things right. So, well, I have the answer, but it's not written in a paper, and it's my fault. It's you need to look at models of the functions that are a little bit that introduce some quadratic, some curvature information that you collect along iterates. It's not only a linear model would not be enough. You need a quadratic model, and this also the bundling will also collect this information negative curvature so that you escape from this region.
Yes, yeah, sort of need to register what's happening with that. Yeah. Yeah, thanks.
You're welcome.
Any more questions?
If I could ask a provocative question, Ascend in the audience. So, what would you do with the co-derivative? You ended your talk with the quote from Claude. These guys in Boston, they have formulas for these things, but they're kind of hard to work with. So
yeah, I like the Clark subdifferential. It's because I can build things with it, and there is calculus, and well, there are things that you can do. I don't have enough knowledge of those co-derivatives, but it would be nice to have numerics to back this kind of very powerful calculus. You know, we need more people working in these kind of things in a constructive, algorithmic way. It's not easy.
There is no calculus for co-derivatives. Once your function is not essentially convex, it's impossible to calculate.
Okay. Well, if you don't have calculus, then you will not be able to do this kind of things. Where are we? That I'm proposing at the end. That would be this kind of. We need to be able to do this kind of calculus, and from there to extract some second order. So my question is. Do the co-derivatives, what is the co-derivative or the second co-derivative of the Moreau envelope? This is my answer, what I would ask. Can you say something about that?
It gets tricky fast.
There's
a formula there, I suppose, but working with it's hard.
Yeah. We need to learn more about that.
Yeah, I think so.
Little by little, we are.
Probably also need a discussion, right? What tools work computationally, because there's a lot of theoretical research and different generalizations. There's thousands of whatnot, subdifferentials, co-derivatives, tangents, and it's unclear what works, what doesn't work numerically so much.
We like Clark.
Well, we like quasi-differentials, but it's not a constructive discussion, right?
No, but it's something that there will be a gradient coming from the black box. It's the information that will be spit by the black box. How do you build something out of that? So any object that you can build that that uses first order information of that type, it will be usable in a black box setting that is the more common in the algorithms. If there is something like the epsilon subdifferential in convex analysis that can be used, then we can use the transportation formula and transport them, and then we can reuse information from one place into another one. That is also algorithmically very useful, so that you don't have all the time to start from a starting point. Is as if your current point is the new starting point, and then you do information, whoop, you throw it, then you go into the other one. You need this continuity to be efficient, for the algorithm to be efficient. So if it is quasi-differential, the answer, I am not in any kind of sect or religion. I take everything. I'm agnostic when it comes to subdifferentials if they build information that is useful. If I can compute things for it.
But you believe in Clark subdifferentials. You are not agnostic.
Because I understand it. I am old school. I'm the 20th century. I'm sorry. So I get the gradient, and I know what to do with the gradient. And also another thing that is important in calculations is convex. I want to project on a convex set. You see. And the Clark subdifferential provides me that. It's this element of minimum norm. That how do I find it? I need to solve. It's a QP in the best, and then so I need convexity of this element. But if by some chance we can build approximations that asymptotically converge to some non-convex object by computing projections on convex sets, maybe it's possible. I don't know. How do you compute something on a non-convex set? A project on a non-convex set?
With a great difficulty, I would say.
Not always.
Question.
No, there's some instances where you can get an exact zero numerical error with a projection
That's
onto.
perfect. That's good. Yeah, that's taking advantage of structure. So
Sure,
there are some situations where you can do it, and then it's okay. It's perfectly, it's fine.
So I would like to thank Claudia one more time, and thank you very much everyone for a very interesting discussion. I feel we have to continue the discussion.